So let's look at a couple where we're going to find the derivative of the function using that limit process. And I want to focus on fraction and then the square root one because those look like a lot of fun. So let's look at that first one. We're going to look at number 25. So we have f of x is equal to 1 over x minus 1. And we're going to go through that limit process to find that definition. So remember, the derivative is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So step 1, find f of x plus delta x. So we're just going to plug x plus delta x in for that x. Step 2 is f of x plus delta x minus f of x. So I'm going to take this and subtract the original function. So we have a fraction minus a fraction. If we want to subtract fractions, we have to have a common denominator. So that common denominator is going to be x plus delta x minus 1 times x minus 1. So I'm going to multiply this guy by x minus 1 over x minus 1. And then I'm going to multiply this one by x plus delta x minus 1. So now I've got common denominators. And you can see what's going to happen here. We're going to have to distribute that negative to everything inside of that second parentheses. So the x terms are going to cancel. The ones are going to cancel. We're going to be left with a negative delta x here. Step 3 is to look at the entire fraction. So I'm going to take what I had in the last step, and I'm going to divide it by delta x. I'm going to think about this as a division problem. And remember, when you divide fractions, you keep change flip, right? So we're going to keep that first one. We're going to change it to multiplication, and we're going to flip that second one. And when we flip that second one, notice those delta x's are going to go away. And then our last step is to take the limit. And when we do that, that term is going to go to 0. So we're going to have this, which is the same thing as this. So there's our derivative. So we would say the derivative of this function is negative x minus 1 to the negative 2. Or if you wanted to, you could write it this way. Okay, what we don't typically do is we do not FOIL that out. And that just creates a big mess. We want to write these as concisely as possible, with everything in a nice factored form typically. So there's that first one. Now, this 4-step process that I'm walking you through for all of these really helps, especially when you have fractions and when you have radicals. I think it just makes it a lot easier instead of trying to do everything in one swoop. So let's look at that next one. We found the derivative for that one. 27, we're going to look at f of x is equal to the square root of x plus 4. So our goal is to find the derivative. The definition of a derivative is the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Step 1, find f of x plus delta x. And that's going to be easy. Step 2, find the numerator of the fraction. Step 3, this is the slope of the secant line. So with a radical, you're going to have to take the conjugate and multiply the top and bottom by the conjugate. So the conjugate of this numerator would be the square root of x plus delta x plus 4 plus the square root of x plus 4. What I do to the top of the fraction, I have to do to the bottom, because math is always fair. So when we do that, we got to think about foiling these things together. So we're going to multiply fronts together. So that square root times that square root is going to be that radicand, x plus delta x plus 4 quantity squared, and taking the square root of that would leave us just with the radicand. So there's my fronts. Okay, notice that the outsides and the insides are going to cancel, because this is really kind of like foiling together a type of difference of squares, if you will. And then last would be minus x plus 4. And that's going to be over delta x times square root of x plus delta x plus 4 plus square root of x plus 4. Now notice here, if we were to distribute that negative, the x's are going to cancel and the 4's are going to cancel. So once again, we're left with delta x on top, delta x times square root of x plus delta x plus 4 plus square root x plus 4. So one thing I want you to notice is that in every single example we've done, that delta x in the denominator always cancels in the numerator. Okay? And that's always going to happen, because if you try to take the limit as delta x goes to 0, and you have that delta x in the denominator, we can't just plug 0 into the denominator, because then we have a problem. We can't divide by 0. So that denominator, that delta x down here, is always going to have to cancel somehow with the numerator. With a radical, the trick is multiplying by the conjugate. In that last example with the fraction, we had to simplify the fraction and combine like terms in order to get that one in the denominator to cancel. See how that happened here? It canceled. Even with the quadratic we did in the last video, it canceled also. So you're always going to see that happen. So now we have 1 over the square root of x plus delta x plus 4 plus the square root of x plus 4. So now step 4, we're taking the limit as delta x goes to 0 of that guy. And that's going to go to 0. So I'm going to have 1 over the square root of x plus 4 plus the square root of x plus 4. And notice I've got 2 of those. So we could write that way. Or we could write that as 1/2 x plus 4 to the negative 1/2. Either way is going to give us the same idea. So that's how we can take that and we can write that idea of a derivative there. Now, every now and then it may be useful to use the alternative form of a derivative. And what this is doing is it's finding the derivative value at a particular point. So you're finding what that slope is of the tangent line at the point. So this is not giving you an expression because you're plugging in a specific number. So let's look at number, let's just do one of these. Let's look at 70. 70 is asking us to find the value of the derivative at 1 for this function here. So if we wanted to do that the other way, we would find the derivative, right, using that limit process, and then we would plug the 1 in. Okay, this is kind of, in a way, a shortcut. It's not going to give us the expression that where we could plug in a whole bunch of C values. It's just finding the value at that one particular C value. In this case, it's 1. So let's go through the process. We're going to... I'm going to write my definition first. I like to do that. It's a limit as x approaches c of f of x minus f of c over x minus c. So for us, it's going to be the limit as x approaches 1 of f of x, which is x squared minus x, minus f of c. So if I plug a 1 in here, I'm going to have 1 squared minus 1. And that's going to be over x minus 1. So we're going to take the limit as x approaches 1. This is going to be x squared minus x. This is going to be a minus 0 over x minus 1. So notice we cannot plug 1 in because if I do, I'm going to get a 0 in the bottom. So that's always a key to let you know that something can factor and reduce. If we factor the top, we see that those x minus 1s cancel. And now we need to take the limit as x approaches 1 of x. And that's just going to be 1. So what this is telling us is the slope of the tangent line at x equals 1 is 1. Okay, and that's the same thing as saying the value of the derivative at 1 is 1. So that's what that alternative definition does, is it finds the value of the derivative at that particular point. It's not extremely useful, but every now and then you'll be able to find a use for it. So let's talk about Theorem 2.1. If a function is if a function is differentiable at a particular point, then that tells us about the continuity at a point. So remember in a pre-calc class when you talked about continuous functions, you said you could basically draw it without picking your pencil up. In a couple of in last chapter, we talked about the definition being a lot more what's the word I'm looking for there? A lot more formal than that. If you think back to last chapter, when we talked about continuity. Three things had to happen. F of c had to exist. The limit as x approaches c has to exist. And just for those to exist wasn't good enough. They actually had to be equal to each other. So f of c had to equal the limit as x approaches c of f of x. So, and this guy's really the big deal, right? That third one. Because if those are equal to each other, then the other two have to happen. So that was the formal definition of continuity. So now we're relating continuity with differentiability. So if it's continuous, that does not mean it's differentiable everywhere. There are places where the derivative doesn't exist, and we'll talk about those in a minute. But if it's differentiable at x equals c, then it's always going to be continuous at x equals c. So just because a function is continuous does not mean that it's going to be differentiable everywhere. There are places where the derivative cannot happen. So what are those places? Places where the derivative does not exist. Anytime we have a sharp corner or a cusp, the derivative is not going to exist. A good example is the absolute value of x. We know that the absolute value of x looks like this. At 0 is where we really have the problem. Over here and over here, it's going to be fine. It's going to be differentiable. But if you look at 0, that's where we have that sharp corner. Okay, corners are coming together in straight line. Cusps will look more like this. So in this case, we have a corner. We have a problem at x equals 0. Think about it in terms of the limit, right? The limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. That's your definition of a derivative. The absolute value can actually be written as a piecewise function. If we were to look at the right of 0, it would be defined as x. If we look at it to the left of 0, it would be negative x. So the real problem has to do with the definition here. For the limit to exist here at 0, that left-hand limit and the right-hand limits have to be the same. But over here, we have a negative slope, and here we have a positive slope. So at 0 is actually where that slope's changing. So we have a problem there because of that. So anytime, and that's going to happen every time you have a corner or a cusp. Anytime you have a corner or a cusp, the derivative cannot exist at that particular place. In this case, it's going to be 0. Okay. You also can't have a derivative exist where you have a vertical tangent. An example would be the cube root of x at 0. So the cube root of x function looks like this. If we were to look at what's going on at 0 we would actually have that vertical tangent. And we know slopes of vertical lines are undefined, which means the derivative would be undefined. So those are examples where you have something continuous and you don't have a derivative. Other places would be, let's say we have a rational function and we have a whole. If we have a whole in the function, there can't be a derivative there. So if we have a function that looks maybe something like this, piecewise function, y equals x squared everywhere except 0. Actually, it wouldn't even be a piecewise function. We would have a whole here. We would not be able to evaluate the derivative there because the function's not defined there. Anywhere you have a vertical asymptote, you're going to have problems also. Like the function y equals 1 over x has a problem at 0 because it has a vertical asymptote at 0. So everywhere else, we could find the derivative or the value of it, but 0 is going to be a problem because the function's not defined. So then just kind of recapping, what does the derivative actually tell you? It tells you 3 different things, right? The first one that we've talked about is the slope of the tangent line. And the slope of the tangent line is actually the instantaneous rate of change, or the instantaneous slope of the function at the graph for that particular point. And then if we're talking about physics, you can talk about the position of something in terms of an equation. I'll call it a position equation. Think about when you take a ball and you throw it up in the air. What goes up must come down on Earth, so it is a quadratic shape. We could model that as what I could call a position equation if we take the derivative of that. That actually gives us the velocity. So not only would we be able to tell where the ball is at any point in time, or missile or whatever we're throwing up in the air or shooting off, but we could also tell you how fast it's going at any particular point in time by taking the derivative of that equation. Now, just kind of a nice little side note here, if we take the derivative of velocity, we'll get the acceleration, so how fast it's speeding up. And we will talk about those kinds of examples a little bit later. So I want you to take a minute, read through these 4 examples, and I want you to describe the values where the function is going to be differentiable. You may want to pause the video, look at these, think about what we've talked about in this video, and then come back and check your answers. So if we look at this first one, number 77, we have x plus 4 to the 2/3 power. So this is an example of a cusp. So notice it's kind of got that little curve in it here, which is why I call it a cusp instead of a corner point. And we're asking, where is it differentiable? Well, it's going to be differentiable everywhere except at that cusp. At that cusp, it's going to have a problem. So it's differentiable except x equals 4. Negative 4, sorry. If we look at that next one, 78, notice we've got 2 vertical asymptotes. So it's going to be differentiable everywhere except those vertical asymptotes. And those are happening at positive 2 and negative 2. And we can see that by setting that denominator equal to 0. 79, we think about where that's differentiable. Well, it's going to be differentiable everywhere except this point here. At this point, it's going to be a little confused. We don't really know how to write that tangent line, the slope of the tangent line, because remember, when we take a derivative, we're actually thinking about a limit. So if we were to think about that alternative form here in terms of a limit, we would think about it in terms of -1, and remember, as f of x minus f of c, which is -1 over x minus c. That limit at -1, for this to exist, the left hand and the right hand limits have to be the same, and we can't do one on this side of the graph. It doesn't exist. So we can't evaluate this. That's going to be a problem. So we would say that the limit doesn't exist here. So the function is differentiable on the open interval from -1 to infinity. Okay. Now notice that the domain is different. The domain is the closed interval from -1 to infinity. So just because a function is continuous doesn't mean it's differentiable everywhere. It cannot be differentiable at a particular point. Now we could go into further detail and talk about left differentiability and right differentiability. This would be differentiable on the right hand side. We don't typically talk about that, though. Those are really special cases. We would say differentiability overall. We would not be differentiable at that particular point because there's nothing to the left of it. And then this guy, 80, we've got this piecewise function. So we are differentiable here and we are differentiable here. The problem is we are not differentiable at x equals 0. Okay, same kind of issue that we had here. Even though we're closed here, we don't know what that tangent line would do. Notice that left-hand limit and that right-hand limit are not the same value. So that's where we would be differentiable.